Welcome back. This is part 2 of the video looking over the answers to the Chapter 7 quiz. I'm going to take a look at the trigonometric identity questions here, specifically the verification of trig identities. The simplifications came in the first video. It's maybe a little tough to fit on this screen, so I'll try to do the best that I can here, but let's see what we've got. Okay, so the first one here, this is problem number 11. You're supposed to verify that secant of t minus the cosine of t all over the secant of t is equal to the sine squared of t. Okay. Now, what I would probably do here is, first of all, I usually try to start on the more complicated side, and I think the left-hand side would be easier to simplify it into the right-hand side than to try to make the right-hand side more complicated to match the left-hand side. Again, different routes you can go here. My personal thought, though, is that the easiest thing to do here would be, since you have a subtraction here in the numerator, remember, as long as you keep common denominators, you can break up addition or subtraction in a numerator. You can't do it in a denominator. That's actually really complicated. But a numerator, you can do that just fine. So I would probably do this as a secant of t over secant of t, which of course is just going to be 1, minus a cosine of t over a secant of t. Okay, and that's going to be equal to a sine squared of t. Remember, the idea is you're getting new true statements each time you make a change. So you really should show both sides each time. And I may not always be able to do that because I'm trying to kind of cram this in on the screen here. But anyway, now secant, and again, you don't really need to write this in necessarily, but secant's the same thing as the reciprocal of cosine. So you actually could move this secant up to the top as a cosine of t, okay? And again, you don't have to show this step. I'm just trying to explain to you what I'm doing. So that's going to turn the second part into a cosine squared of t. Okay, of course, this is going to be 1. I usually encourage you to make one step per, basically to do one step per line. Again, to try to fit in the video here, I'm going to do this in one step. So 1 minus, that'll be cosine squared of t is equal to sine squared of t. And then we know from the Pythagorean identities, if sine squared of t plus cosine squared of t is equal to 1, then 1 minus the cosine squared of t is going to be equal to the sine squared of t. So remember, you're always ending with a true statement there, with the right side equaling the left-hand side. And that's what we've got as our final. So you can kind of see that it verified. So they may not be fun to do, but the nice thing is once you get a right answer, you're always relatively sure that you did the problem correctly because the pieces all have to fit. So that's what's going on there. All right, number 12. It is a tangent of y on top over a cosecant of y. Sorry, that's not very legible, is it? Is equal to a secant of y minus a cosine of y. And I initially started on the left-hand side. That just looked like it would be easier to work with. I was a little bit confused on the left about how I was going to get subtraction into the problem. And so as a result, I actually ended up going to the right-hand side and trying to change that side instead. And I thought, you know what, secant's 1 over cosine. Basically, I could get a common denominator and kind of go from there. So that's what I ended up doing. So I'm keeping the left the same. And on the right, I'll write the secant as 1 over cosine of y minus the cosine of y. And now I'm subtracting 2 fractions, so I could get a common denominator and subtract the 2 fractions. Again, you don't have to write this step in, but I'm going to kind of scribble it over this just to show you what I'm doing. This cosine of y, of course, is cosine of y over 1. I need a common denominator to be cosine of y, so I'm going to multiply the bottom by cosine of y. I multiply the top by cosine of y, and that would end up giving me a cosine squared of y over cosine of y, which we'll be able to work with from there. So anyway, we end up with the tangent of y over the cosecant of y being equal to 1 over cosine of y minus cosine squared of y over cosine of y. Okay, and I'm running out of space here a little bit to be able to do this, but notice now we have a common denominator. Okay, so we're going to have a 1 minus cosine squared on top. Okay, and then on the bottom you're still going to have a cosine of y. So that's going to be, and I'm running out of space to write that left-hand side there, so I'm not going to do that. But that's going to be a 1 minus cosine squared of y on top over a cosine of y on the left when we put that together. Okay, and since I'm almost out of space here, I'm going to move back up to some of these higher levels here from earlier and see if I can write the other steps there. So this should actually continue. I just don't have room to actually continue. So anyway, so we're going to have tangent of y over cosecant of y on the left. And that's going to be equal to, now 1 minus cosine squared of y is the same thing as sine squared of y. And you're going to write that over cosine of y. And this is where this will come together. So we're really close now because we've got two fractions and they just have multiplication and division. So they're the right form. They're just not quite the right pieces. So I'm going to break up this, this part on the right here. That's going to be a sine of y times another sine of y, and I need to have one cosine of y in the bottom. And then I realize, oh wait, I need a tangent. Sine of y over cosine of y is tangent, right? So, so I'm just going to write this over the cosine of y. Okay, and then of course the left-hand side still doesn't change. And you can see there we have a tangent, and the reciprocal of this is cosecant. Okay, so I guess, again, really it should be two lines, but I'm going to write this as a tangent of y over a cosecant of y is equal to, that's going to be a tangent of y. This is going to move to the bottom as a cosecant of y. And then we have our statement checking out. Okay, so that's number 12. Hope that was helpful. If not, maybe you can go look at it again. All right, moving on to number 13. Number 13 looked like it was going to be really complicated because it has fourth power things in it. It's a secant to the fourth of x minus a tangent to the fourth of x. And it kind of looked a little bit like a Pythagorean identity because we've got one for secant squared and tangent squared, but obviously it's not the same thing. So I'm not sure what's going on with that, but anyway, kind of thinking about that in the back of my head, it's going to be equal to secant squared of x plus tangent squared of x, okay? I noticed that that was a difference of perfect squares, okay? Secant to the fourth is secant squared, tangent to the fourth is tangent squared of x squared. So I used a difference of squares factoring pattern here. I wrote this as a secant of secant squared of x minus a tangent squared of x times the secant squared of x plus a tangent squared of x is equal to a secant squared of x plus a tangent squared of x. Okay, and I'm kind of looking here, and I'm noticing that's a squared, by the way. I'm noticing we've got a trig identity that has a secant squared and a tangent squared, right? That's that secant squared of x is equal to 1 plus the tangent squared of x, and we want secant squared minus tangent squared. Well, if I subtract tangent squared from both sides, I'm going to get the secant squared of x minus tangent squared of x is equal to 1. So that whole thing there is actually just equal to 1, which is fantastic, because then you just have 1 times the other set of parentheses. If this is just 1, then 1 times this is just going to leave me with secant squared of x plus tangent squared of x. And that's exactly what I wanted. Okay, it's going to be equal to secant squared of x plus tangent squared of x. Okay, so anyway, be on the lookout. If you see something that looks like a difference of squares, try factoring it. Very often you may get something that cancels, and a lot of times you end up with some Pythagorean identities coming into play, which can really make your life a whole lot easier. This doesn't want to erase. Hang on just a second here. erase a bunch of it. Okay, there we go. All right. And let's see, we have the last of the trig identities, and we've got two equation solving ones. And the bonus was kind of hard for what we've talked about, so I don't think I'm going to do that on the video. I'm not even sure if I'm going to do that in class, actually. It's very much beyond what we had discussed, and actually requires a calculator to be done, which I didn't imply that you were going to need a calculator for anything on this. All right, so the last one here, we're trying to show that the sine of a over 1 minus the cosine of a minus the cotangent of a is equal to the cosecant of a. Again, I've got fractions on the left. I've got a difference on the left. I've got none of that on the right. Okay, so I'm thinking, I'd like to get rid of my fractions. I'd also like to get rid of the subtraction. To be able to do a subtraction, I'm going to need to have a common denominator, I think. And so that's the kind of thing I'm thinking. So if I look at this fraction on the left here is close to 1 minus cosine squared of a. 1 minus cosine squared of a, of course, is equal to sine squared of a, but it's not squared. And I can use the difference of squares patterns, okay? If I multiply the bottom by 1 plus cosine of a, and this, again, doesn't really need to be shown in your proof. This would be like your work on the side. Now, it's a fraction, so I also need to multiply the top by 1 plus cosine of a. Okay, what I'm going to end up with on top, I get something that doesn't look simple in any sense. I get sine of a plus sine of a cosine of a. On the bottom, though, if you FOIL that out, you get 1 minus cosine squared of a, which is the same thing as sine of a, which I think is going to be helpful. Now we have minus a cotangent of a, and cotangent is cosine of a over sine of a. So I'm going to go ahead and write it in that form. And I want this to be equal to the cosecant of a. Okay. And right now it's still a huge mess. Okay. However, the denominator on the left, this is the same thing as sine squared of a. And I really should put that in my next step. I'm just kind of showing you that's what I'd be thinking about. And meanwhile, if I could get a denominator of sine squared of a for the second fraction, I could subtract the 2, and I'm hoping that something magically kind of simplifies down a little bit. So I'm going to multiply the top and the bottom of the second fraction also by sine of a to get a common denominator. Okay, and again, I'm really doing this, really should be 2 separate steps, but I don't have that much space in my video. So anyway, we're going to end up with sine of a plus sine of a cosine of a. I'm replacing 1 minus cosine squared of a with sine squared of a. And that's going to be minus sine of a cosine of a all over sine of a. And we'd like to show that it's equal to cosecant of a, which, move myself up a little bit here, equal to cosecant of a. Okay. Again, it's big, it's messy. I don't have enough room to do all of this, so let me clear myself up some space here. All right, so if you take a look at that, we've got 2 fractions with common denominators now. Oh, I'm sorry, that's supposed to be a sine squared of a on the second bottom there. I multiplied the bottom by sine of a. So you should be able to subtract those 2 numerators. And if you notice, you have a sine of a cosine of a and a minus sine of a cosine of a. And those guys are going to cancel. You're going to be left with just a sine of a on top. On the bottom, you're going to be left with a sine squared of a. And then you want to say that's equal to cosecant of a. Okay, well, that's going to be 1 over sine of a. And 1 over sine of a, of course, is equal to cosecant of a. And that'll kind of close things out. So it still technically is a couple of steps, but it's pretty easy steps. So that simplifies down to 1 over sine of a is equal to cosecant of a. And 1 over sine is equal to cosecant. And everything works out and it checks. Okay, so kind of tricky, a lot of things going on, a lot of steps, a lot of things you have to show. All right, there were 2 other questions that I'm going to look at, not looking at the bonus. Trig equation problems. So we had the tangent squared of x plus the tangent of x is equal to 0. And you're asked to find any solutions between 0 and 2 pi. It actually says between 0 and 2 pi. I believe it should have been values greater than or equal to 0, less than 2 pi, like 0 up to 2 pi. Since 2 pi, you're just repeating 0 essentially on the unit circle. Anyway, I looked at this equation and I noticed, first of all, if it equals 0, if you can write it as a product, if two things multiply to be 0, either the first has to be 0 or the second has to be 0. And so I noticed that there was a greatest common factor of tangent of x, and I factored that out. And that gave me tangent of x times the quantity tangent of x plus 1 is equal to 0. And then I realized, oh, well, this is multiplying by this to give me 0. So either tangent of x has to be 0, or tangent of x plus 1 has to be 0. And I just have to solve those two equations in the range between 0 and 2 pi. So that's what we're looking at here. And I think one of the tricky things about these problems is you don't often come in knowing how many solutions you're going to have. And by the way, if you have time, I would make a graph and check and see that these are actually showing up between 0 and 2 pi. Make sure you're in radians when you graph it. Hopefully you remember what the tangent function looks like. The tangent function, of course, goes through the origin, and it is a horrible picture. It has asymptotes at pi over 2 and negative pi over 2, and continues to have asymptotes every pi radians. My point being here that tangent of 0 is 0. So 0 is one of our solutions, okay? And then the tangent function repeats every pi radian, so 0, pi, and again, I wasn't real clear about whether or not the 2 pi needed to be included or not. So you get another pi radians, and it'll also be equal to 0 at 2 pi. Tangent of x plus 1 equals 0. That's the same thing as saying that the tangent of x is equal to negative 1, okay? Tangent, when you're working with the unit circle, is an opposite side over an adjacent side, or you could say it's a y over an x. Actually, y over x if you're working with the unit circle. It's going to be negative 1. That means y and x have to be the same, but it's in a quadrant where you have a negative tangent function. So the x and the y on the unit circle are going to be the same anytime your reference angle is 45 degrees, or actually we're working in radians. So it would be anytime your reference angle is pi over 4. Okay, and we would like it to be negative 1. Okay, well, if you look at this, that's going to be, of course, the tangent function is negative in the, let's see, all students take calculus. It's going to be negative in the third quadrant, and it's going to be negative in the fourth quadrant. Okay, so a reference angle of 45 degrees in the second quadrant is 135 degrees, which is 3 pi over 4. Okay, and a reference angle of 45 degrees in the fourth quadrant is 315, which is 7 pi over 4. Okay, and again, I believe if you graph that, you're going to see, if you're in radians, if you have your window setting set up going from 0 to 2 pi radians, I think you're going to see it cross the axis in 4, maybe 5 places, depending on whether or not you're counting that 2 pi or not there at the end. Okay, and the last of our equations, I think the last equation was actually simpler than this one. At least that's my hope. Let's see here. The last one is 4 sine of x is equal to 2. Divide both sides by 4. You're going to get sine of x is equal to 2 over 4, which is, of course, 1/2. And that's one that a lot of you, hopefully at this point, know off the top of your heads. We're looking for places that have a sine of 1/2. That's going to be a reference angle of 30 degrees in quadrants where the sine function is positive. Okay, so 30 degrees is the same thing as pi over 6 radians. Sine function is also positive in the second quadrant. A 30-degree reference angle in the second quadrant would be a 150-degree, or in radians, that would be 5 pi over 6. And those end up being your two solutions. So anyway, both of those, I think it's pretty easy to get some answers right. I think it's pretty easy to make mistakes or get the wrong number of solutions or that sort of thing. So I think that's where this is a little bit challenging. And that's why I do encourage you to consider making a graph and just checking and seeing if your answer makes sense based on the graph. But anyway, I hope seeing those gone through a little bit more carefully will be helpful for everybody in getting ready for the test next week.